Hi, everybody. Thank you so much for being here and for attending our workshop. zkApp is really cool, so thank you for them to having thank you to them for having us. And today we're going to be talking about SnarkyJS and the Mina Protocol. So there we go. First, a little bit about me. My name is Jack Servia. I live in Denver, and I'm a developer relations engineer for ON Labs. So I end up doing some engineering work, some DevRel stuff like this, and then also some business development and other stuff. You can follow me on Twitter at Jack Servia. And so what is O of One Labs? O of One Labs is basically a zero-knowledge proof technology company, and we built the proof system for the Mina Protocol, the reference node implementation, and now SnarkyJS, the smart contract language for the Mina Protocol. Our relationship to the Mina Foundation is kind of like that of Ethereum Foundation to Ethereum versus consensus to Ethereum. We're kind of like the consensus to Mina Protocol. And so here's what we're going to talk about today. First, we'll run through SnarkyJS, kind of briefly what it is, why it's interesting, and what you can do with it. And then we'll talk about the Mina Protocol, which is this layer 1 blockchain that we can deploy these SnarkyJS smart contracts to. And it has a whole bunch of other interesting properties. And then finally, we'll dive into 2 code examples. So first, we'll build a Wordle game, and then we'll actually make it recursive, which means that we'll be able to play this game without sending any transactions to the Mina network until the game is over. And so this way, we don't have to wait for blocks to get mined or pay transaction fees every time that a user makes a move. We just sort of exchange these proofs between the 2 users, and then eventually we have a final proof that attests to the validity of the entire game, and we send that on to the Mina network. And then we'll have a little bit of time at the end, maybe 15 minutes for questions and answers, and to talk about where you can learn more. I guess kind of a meta thing is that there's a lot going on here. We've built a whole new blockchain, and it's very, very different from many existing blockchains. And so this presentation will kind of try to introduce you to all the things that are interesting and cool about it, and give you a sense of what it looks like to build applications on it. But it won't be comprehensive by any means. And so we have things like office hours and good documentation. There's all sorts of ways that you can learn more, after the presentation. So if some things sort of slip through the cracks, that's perfectly okay. The point is to give you a kind of a high-level understanding. Okay, so on to SnarkyJS. It's a TypeScript library for defining zero-knowledge proofs. And it's also the smart contract language for the Mina Protocol. You can use it without the Mina Protocol, and then when you use it with the Mina Protocol, it sort of acts like, I don't know what the analogy would be. It's basically a smart contract on the Mina Protocol is a superset of a SnarkyJS program. It looks like this. So you can see this looks like something that you can probably learn. It's TypeScript, and it's pretty idiomatic. And so you can keep using the tools that you're familiar with. You can use, VS Code, ESLint, Prettier, NPM, all the good stuff. We don't have to reinvent the wheel with a lot of this developer tooling because it just already exists. And it's very easy to learn. We have super good IntelliSense doc comments, so you can actually probably dive into a code base without looking at docs or anything and get a feel for what's going on just by hovering over anything that sort of sticks out that you don't know what it does. And this is actually probably a good way to get started if you want to, is just dive into a code base and start poking around at things. We also have very good documentation and tutorials and office hours and all sorts of resources to help you get up to speed if this doesn't work as well for you, but this is definitely an option for SnarkyJS. SnarkyJS is also extremely powerful. This is for 2 reasons. One is Kimchi, which is our proof system. So we've built this kind of from the ground up. Obviously, it is sort of informed by the design of other proof systems that are state of the art today. And it has a number of unique features that make it really well suited to our use case. So the first is fully trustless setup. We have custom constraints for Poseidon, elliptic curves, and encryption, and we can add more of these. And so these, if you're sort of not familiar, are kind of like, you can think of it as like almost hardware acceleration inside of your zero-knowledge proof. So instead of having to kind of program things directly, you can sort of just like call into this thing that already exists inside of the framework. And there's really significant efficiency gains here. So, hash functions, for example, we can build much larger Merkle trees. It's not just that it's faster, it's that it actually opens the door to being able to do things that might not be possible in another ecosystem. Our proof size is constant, thus the O of1 Labs name, constant size and constant computational complexity to verify. It's recursive. It's infinitely recursive, and we can branch and merge arbitrarily. So what this means is that we can create a zero-knowledge proof and then verify it inside of another zero-knowledge proof. And that first zero-knowledge proof is the same size as the second zero-knowledge proof that it's verified inside of. But what we can also do is we can verify like 5 zero-knowledge proofs inside of one zero-knowledge proof. And that top-level proof is the same size as each of its constituent parts. And so this is really cool for scalability. And it also opens the door to being able to do a couple of other unique things. You can do things like run smart contracts asynchronously. You can attest that a sort of a process has been going on correctly for an extended period of time without having to remember all of the history. And so I'll talk more about this later. And then finally, we use a Planck-Kush arithmetization, so we can add new features sort of as that kind of part of, I guess, like research moves forward. So we have things like dynamic array access that we're working on right now. And so the point of this is just that we've put all the horsepower that we can inside of SnarkyJS. It's really state of the art. And so, like under the hood, we have, everything you could want. And then when it comes time to use it, we've actually, also tried to empower people sort of on like the developer side. The thing itself is very powerful, and the interface to it should be very powerful and sort of expressive as well. And so there's just a few things I'll highlight here. The first is that we have, method chaining, which makes the programs sort of easy to think through. You can think about, what is my data? How do I want it to change? And then, what do I want to do with it after it's changed? And this makes it simpler to ensure that you're, writing smart contracts that are fully constrained and just easier to think about in general. You can see what this looks like. We have here we've got is not red peg is in this case going to be a Boolean, and we get this by accessing this value in index I of guess, checking if it's equal to 0, and then also calling this not method on that. And so if guess I is not equal to 0, then is not red peg is true. This should look pretty familiar and kind of not too fancy, and that's kind of the idea, is that it's very much like the kind of things you've used before. And even though it kind of looks simple, it's actually pretty complicated to make things work this way. And so we've put a lot of effort into making it feel like something that you've used before. Another feature that's pretty cool is that we have structs, and these are what they sound like. They provide a layer of abstraction that makes your data quite a bit easier to think about. And so you can see here we define a struct, my struct pure, and it has some different values on it, and each of these values, are themselves structs. Not necessarily literally. When you dive in deeper, some of this stuff again is kind of like built into the proof system, but you can think about it as each of these values being structs, and you can compose structs from other structs. And so one of the kind of fundamental requirements of zero-knowledge proof systems is that of all of them is that data has to be represented in this field type. Field is like a it's an element of a finite field, which is kind of like a complicated set of numbers, basically, that have properties that are pretty familiar for the most part, with a few caveats, and they're kind of big caveats. Things like division work quite differently. And so this can be confusing for people. Now, it's also very efficient, so there are reasons why you would want to use it, but SnarkyJS gives you the ability to compose these field types into structs, and then compose those structs into even more abstract structs, and so on until you get a data type that works like you expect it to, and kind of feels natural. And so you can see we can do things down here like pass these structs into a method of our smart contract, and we'll kind of get into that in a second. And then finally, a lot of the stuff that you need is already implemented in SnarkyJS, and we're working on implementing more things every day. And also, if you're a member of the community who wants to add something, that would be awesome. We're super interested in getting the community contributing even more than they already are, adding these little features and stuff. And there's grant programs that I'll talk about after that can help incentivize that kind of behavior. So we have all of these different types, or you can think of them as structs, as we sort of talked about earlier. Some of them are, again, implemented way deep down in the proof system for the sake of efficiency, but they behave exactly the same as structs. And so we have these for unsigned integers, Boolean scalars, public keys, private keys, signatures, and we have more coming soon, including things like string and a few other types. We have efficient Poseidon hash function. So this again means that we can not only do things faster, but we can do more things. We can build larger Merkle trees than you could build in a different framework, and this is really powerful. We have efficient encryption and decryption, also very powerful. We can pass encrypted values into our smart contract without it being a huge number of constraints. We have efficient signatures. And then we have an API for Merkle trees, actions and reducers, and a few other kind of more complicated structures that you wouldn't want to implement yourself, but that you might need to use. And then finally, we have the Recursion API, which makes building these recursive proofs much easier. A question that we get asked a lot is why we chose TypeScript, and lots of people have strong opinions about it. But the truth is that it's sort of quite good at this point in time. I think a lot of the kind of jokes about JavaScript, originated like 10 years ago, and it was more confusing than it is now. There was sort of like obvious features omitted that would be good, and some idiosyncrasies that have kind of been rectified since. But the real reason that we chose TypeScript is because we're ecosystem focused. And so we really think that there's a huge amount of value that we can capture by, or not even capture, just create, by basically connecting people who want to work on very complicated, powerful, magical crypto stuff with people who want to build user-facing products. Something like Dark Forest is kind of an example of this, where you have kind of two sides that create a really, really unique and powerful, cool new thing. There's this kind of cryptography problem side, and then this let's build a game side. And usually these kinds of people don't interact as much as it would be nice if they did. And so the idea of SnarkyJS is that somebody can build a crazy complicated crypto library. They could be incentivized by a DAO or a grant or something, or do it just for fun. And then they can just npm publish it or put it on GitHub, or however they want to distribute it. And then when somebody comes and they want to build a user-facing product, they can just npm install this library and get going. Yeah, we hope that we kind of get people working on both sides of this, and that the result is super cool projects, like things like we have a thing called the zkApp Builders program, and it's what it sounds like. It's a program where we help get people up to speed building zkApps, and then hopefully they build really powerful things. And so one of the participants in the program, this cohort, which just closed up a few days ago, built like a bunch of primitives for games like card shuffling. And so card shuffling is pretty hard. It's like a kind of a hard crypto problem, at least for most people. And so by just having this card shuffling library available, now anybody who wants to build a card game can have a shuffled deck without having to figure out like all the complexities of this, like how do I prove to you that I shuffled my deck correctly without me knowing the order of the deck or you knowing the order of the deck. So that's really powerful. This is kind of a rehash of that. This is for in case you want to go back and look at the slides after. There will be a link to them. Maybe it's already been shared, but kind of a rehash of what we went through. Okay, so how does SnarkyJS work? Here it is in 5 sentences. This is a really high-level explanation, and there's a bit of abstraction. It's not like entirely accurate, but it's a good sort of place to start your understanding. And then if you're curious, you can come to office hours or something and learn a little bit more. So it's a TypeScript library. There's no sort of other component to it. It's standalone. And all of the information in a SnarkyJS program is represented in one of these compatible types, which is either a field or a struct that's composed of fields. And the idea is that if we operate on like a number or something, we can't necessarily, like a JavaScript number, we can't necessarily prove that we've done this correctly. But by using these SnarkyJS compatible types, anything that we do using one of these SnarkyJS compatible types, we can prove that we've sort of done it in the way that it was intended to be done. And so we represent all of our data in our program using these types. And then SnarkyJS provides classes and functions on these types, or just as standalone things that you can import, and they're compatible with the field type or the structures that are composed of them. And so you can do something like add two fields together by calling the add method on one of these field types, and then passing another field type in as an argument. And so when you do this, it does what you expect. It adds the two fields together, but it also does it in such a way that later on it can prove that it did it correctly. And that's kind of where the magic happens. And so any of the operations that we do on these field types can be represented as this kimchi arithmetization, which is basically a big math problem that represents our program. And then this is what we actually use to generate the zero knowledge proof. So when a user interacts with the SnarkyJS program, they can basically remember all of the values of these variables that they've used within the course of their program, and then they can pass them into this math problem and do some other stuff and basically get a zero knowledge proof that their interaction was allowed. So that's how a SnarkyJS sort of program works. But how do smart contracts work? So developers write the smart contracts in TypeScript, and they deploy the verification key to a zkApp account. So they write the program, they call a method that generates a verification key, or more likely than not, they use our developer tool, the zkApp CLI, and it'll just do this automatically. And we'll actually do this at the end of the presentation. And so then they send this verification key to the Mina Protocol in a transaction. And the verification key goes on and gets added as like a piece of metadata to an account. And then when it comes time for users to run the smart contract, they just run the code normally. They get it from a CDN or IPFS or some sort of data availability layer. Wherever they want to get it. It could even be stored like on a flash drive. It's just TypeScript code. And so they run it in their browser, and then after they're done running it, they generate this zero knowledge proof of their interaction that proves that they ran the code correctly. And so even if they do something like change the code, they just won't be able to generate a valid zero knowledge proof. This is like entirely robust. There's no sort of security concession relative to something like the sort of Ethereum model where you have a bunch of nodes do the thing and the user requests that the nodes do something. And so the user runs their smart contract. They get a transaction, which is basically a zero knowledge proof and some other data, and they send this to the Mina network. And if the zero knowledge proof is valid, then Mina accepts the transaction, and if it's not, then it drops the transaction. And if it does accept the transaction, then what it also does is it commits any relevant state updates. So when we generate our transaction, when we run our code, we might generate something like an event that we want to emit or a value on chain that we want to change. And these are associated with our proof. And so if Mina can validate the proof, then it just sort of blindly, not actually blindly, it knows that everything happened as it should have by the zero knowledge proof, but it can just basically validate the zero knowledge proof and then do whatever other things the user says. And it knows that the person can't make a valid zero knowledge proof unless they're requesting things that are legal. And so, yeah, it just gets like a list of events it should emit, updates to state, whatever. And so here's kind of what this looks like. We have the smart contract method, and we pass into it this is sort of like a superset of this zero knowledge proof program idea. We have a zero knowledge proof program where we've defined some of the functionality and the logic ourselves, and then we have some other logic that handles things like how does this smart contract interact with the state of the world and the state of other smart contracts, that kind of thing. And so what we end up passing into our smart contract when you call it, basically, and this is abstracted away from the user, they just pass in the same things that they would pass in to a normal like an Ethereum transaction. But under the hood, we pass in the arguments that the user passed in, these method arguments, and then we also pass in the state of the smart contract at the time that we're generating the proof, and then we also pass in some states from the outside world. So this could be like block height or something like that. And we pass all these things in, we run our smart contract method, and we prove that we did it correctly. And what we get out is this list of updates, and like these are state updates, events, whatever, and then updates to the state of the world. So this, I guess would also be like events, permission changes, that kind of thing, and a zero knowledge proof also. And so we send the zero knowledge proof and these two lists of updates to the blockchain. And if the zero knowledge proof is valid, then we apply these two updates. This is again kind of a rehash. And so now let's talk about how zkApps work. So we have we have programs and we have smart contracts now, but how do zkApps themselves work? And it's actually really simple. You just install the smart contract into your UI repository, and you deploy it, and that's it. The smart contract is just TypeScript code, so you can do whatever you want with it. You can run it in Electron or Node or a browser, and you can call into it from your UI code, just like you would call into any other library. And so yeah, you can publish your smart contract as a library or an npm package. Again, it works just like normal JavaScript code is kind of the idea. And we have a tutorial on this too. So okay, that's SnarkyJS, but what about the Mina Protocol? The Mina Protocol, sort of the consensus of it is pretty complicated, and so if you want to go dive into that, again, we have docs for it, office hours, and you can also read the white paper, that kind of thing. But we'll kind of give you like a high-level idea of what makes it different from other protocols. So it's a layer 1 blockchain, and it proves its entire finalized state using these recursive zero-knowledge proofs. This is really unique because it means that the amount of information that you need in order to verify the current state of the Mina blockchain doesn't grow. So with a blockchain like Ethereum, you basically need to remember every single transaction and kind of sum them together in order to get to this like final like edge of that kind of like transaction history, which is the part that's true. And this means that Ethereum nodes grow over time, and that it's very hard to basically make an Ethereum node that only sort of validates a part of this state. It's really all or nothing. And this means that people in practice end up using things like Alchemy and Infura as endpoints, and then just RPC calling them from wallets that don't really do anything. So with Mina, we have this 22 kilobyte blob, and what this really is it's the state root for the Mina blockchain, a proof that we got to the state root via a valid sequence of transactions. I'm sorry, via a valid sort of application of the consensus protocol, and then also we can include any actual state that we want to use. And so for like a block producer node, you might record the current state for every account. And this would mean that your node size doesn't grow relative to time. It grows just relative to the number of accounts on the blockchain. And so that's really nice. This means that it's very fast to spin up a node. Anybody can do it. And these nodes have all the account information, so they can generate transactions. But we could also do something like make a single account node. And so this would store just, again, this proof, the state root, and then a Merkle path down to a single person's account, and then all the information for the account. And so that's all that you would need in order to like generate your own transactions and basically not need to connect to some sort of other endpoint like Infura or something. And then there's also another kind of node that I guess I'll just touch on here, which is called an archive node. And this is a node that just remembers everything. And so it doesn't, this isn't required for consensus, but sometimes this is something that's nice for like a block explorer, or if you want to do like analysis of like previous chain history. This is another thing we get lots of questions about, so feel free to drop into office hours or something if you need more clarification on this. Okay, so this is a very different way of doing things. And I guess I'll also kind of explain how this works. So instead of summing up all of our signed transactions, what we actually do with Mina is we have basically a zero-knowledge proof that represents the validation of a bunch of transactions. So the transactions themselves are zero-knowledge proofs, and then we validate them inside of another zero-knowledge proof. And then when we want to add more transactions, we can basically just validate these new transactions, which are zero-knowledge proofs, and also the last batch of transactions that we validated, which is also a zero-knowledge proof, and get another zero-knowledge proof out. And so once that's done, we can drop all these previous transactions and the zero-knowledge proof that aggregates them, because it's attested to inside of this new zero-knowledge proof. So we can just do this over and over and over again. You can kind of think of it as like taking a picture of a picture of a picture of a picture of a picture. If I wanted to prove that I like went to the park every day, I could go to the park, take a picture, go to the park again the next day, hold up the picture of the last day, take another picture, and do this over and over again. And that's kind of how Mina works. This is like a high-level abstraction. It's not exactly how it works, but I think it gets kind of like the general idea across. And so, okay, is this cool or is it useful? And it's both for a couple of reasons. The first reason is privacy. So an Ethereum smart contract runs on every single node so that all the information is public. And, it's required to work this way by kind of like the, I guess, like the assumptions of the consensus mechanism. We call some sort of method, and then every single app does our call for us. I'm sorry, every single node does our executes our call on our behalf. And so it's very hard to build private applications in this way. But with Mina, the smart contract runs in the browser, and the arguments in the intermediate values are private by default. So that makes it much easier to build something like private DAO voting or some sort of limited information game or verifiable credentials or, the list goes on and on. And I guess I should also highlight here that the SnarkyJS and the Mina Protocol are designed in such a way that the users prove these things themselves. Your browser does the work to generate the proof and sends the proof off to the Mina network. So it's not like I run the smart contract and then I sort of like send something off to like a data center somewhere that then does this final kind of like proof generation step. We generate the proofs ourselves, and our proof system is efficient enough that this is feasible and a relatively good user experience. So yeah, this is really, really cool. The thing that's not private, I guess I'll also highlight, is the on-chain state. Now, this isn't a problem, and it has to not be private. This is like kind of like a fundamental requirement. Like, where would you put the private key if you had encrypted on-chain state? Basically, it has to live with sort of a relevant person, and if one person has the private key for all the chain state, then that person controls the network basically. And so what you can do to kind of get around this is you can store commitments to things. So like if I want to have, like, let's say I have a piece in a game and I want to commit to the place that it is so that I can't like teleport all over the place willy-nilly. But I also don't want to tell anybody where I am. I can, take my location, let's say it's an X and Y coordinate, and hash it and store that hash on the blockchain. And then the next time that I want to make a move, I can pass in my location and we can check if that location matches the hash that we have stored on chain, and then make our move, get to a new location, and then hash that and store that on chain. Again, if there's questions, feel free to ask at the end or come to office hours. Okay, so yeah, the user runs their method themselves and they send just this state update and the proof to the blockchain. And so the blockchain just verifies the proof and updates the chain state. It doesn't actually have to know exactly what you did. It just needs to know, what do we want to change, and did we do something that allows us to change these things. Another thing that's very different about Mina is kind of the way that you can scale applications. So there's no gas model. zkApps run off-chain, and the amount of computation doesn't affect the transaction cost. So you can do a lot of computation or a little bit of computation, and no matter what, all that Mina has to do is verify the zero knowledge proof, which is always the same size, and it's very easy to verify. The other thing that you can do is you can build these application-specific rollups using recursion, so that you can actually do an unlimited amount of computation. Like if I wanted to prove that I had kept the correct moving average of, I don't know, the price of some sort of asset for an extended period of time, I could prove that I did it for the last, hour, verify that proof, and then prove that I did it for the next hour, verify that proof and prove that I did it for the next hour, and so on and so on. And I can forget all of the prior proofs. I just need the most recent one. And so, this means we can do, an unlimited amount of computation and have this proof that attests to the fact that we did it correctly. So these application-specific rollups, maybe kind of think Cosmos app chains with some other cool features, somewhere between app chains, zk rollups on Ethereum, and kind of some stuff that's all its own. But it's very powerful, and this is actually what we'll do with the Wordle example later. Oh, sorry, it looks like we skipped a slide. So the other thing that's different is decentralization. So because it's possible to validate the entire Mina state using only the small zero knowledge proof, there's no need to rely on trusted third-party node operators like Infura. Now, this isn't exactly like practically true today. It's true in theory, but nobody has built a wallet that does this yet. You can imagine that it's a bit more complicated than building a normal wallet, because you're kind of building something that's somewhere between a node and a wallet. But ChainSafe is working on this right now, and I think they have a demo if you go to their GitHub for it. So yeah, theoretically possible. People are working on making it practically possible, and theoretically impossible for all other blockchains, as far as I know. Another thing that we can do differently is bridging. So smart contracts on other chains, they can bridge the entire Mina state just by verifying the most recent proof. And so we can do something like write an Ethereum contract where a user can call it and pass in as arguments our proof and the state root for the Mina blockchain. And the smart contract can just verify the proof and then know that the state root is correct. And so, you could add some other logic that says, like, as long as this proof and state root are for a block height that's higher than the last one that the contract is remembering, update. And so in theory, anybody can do this then, right? We have the whole Mina state root attested to in this root node, and then, a proof, and we can verify this proof on Ethereum and bridge the whole Mina state over. And again, this is something that's not possible in practice today, but well, I guess it is sort of possible in practice, just not on mainnet. So the NIL Foundation is working on this from a joint grant from the Ethereum and Mina Foundation, and this is a smart contract for the EVM architecture that will let you bridge the whole Mina state over to another chain. And so they have an example. I think we have a link to it also at the end of the presentation. And you can experiment with this. It works today for bridging to, I forget which testnet, but one of the testnets, one of the Ethereum testnets. Finally, oracles work a little bit differently. So users will be able to create zk oracle proofs that bring data from any website onto the Mina blockchain. And I don't know a lot about how this works specifically. It's kind of complicated and has like a sizable MPC component. But we have a couple of people at ON Labs who are working on this. And sort of practically what it will allow you to do is go to a website, prove that you went to this website on, at a certain time, and that it responded with some data. And so then you have this non-interactive proof that you can pass as an argument into, a smart contract, or even just give to somebody. And so you can do something like go to, let's say, your bank account website, look at all of your personal information, prove that you went to your bank account website, that your bank account website is kind of like the real one, I guess, like that the person who sent it to you really has the certificates for that institution. And then you can also prove some things about context. And so then we have this proof that says we went to our bank account website, and we can actually pass it in as an argument to another proof that can do something like check, I don't know, is my credit score above some certain threshold or something like that. And so we can obfuscate this data, and then we can just have a proof that says, hey, I'm a unique person and I have a credit score above X, therefore maybe I can get a loan, or something like that. Or, I'm over the age of 21, anything like this. If you're curious about this, also come to office hours. I won't dive in too much about how it works because I'm not sure that I'll say things that are exactly correct, but very interesting feature. Also not live today, but we're working on it and hope to have it live soon. And it should be, really disruptive. So what else is possible? Well, we actually don't know everything that's possible yet. And this is why we do things like zkHack and hackathons and other stuff, is so that people, we can get a lot of minds together and kind of explore all the different avenues that this has opened. Probably like once a month, we find something that's really cool and really powerful that we didn't know was possible the month prior. And by getting more people involved, we hope that you guys are able to also find, really novel solutions to problems, and then, work towards implementing them together. Okay, so here's kind of a rehash again, and now we'll get on to the Wordle example. So I'll switch my screen share real quick to this. And so this, we have a link to this repository on, I think in the chat right now. This is, oops, sorry, what did I do? This is a Wordle game. I don't know, probably most people have played Wordle. If you haven't, it's a game that basically there's a 5-letter word, you guess what it would be, and you get, based on your guess, some of the letters in your guess get either filled in green or yellow. And if they're green, it means that you have the correct letter in the correct place. And if it's yellow, then it means that you have the correct letter, but not in the correct place. And so this is something that would be hard to build on another blockchain because how would you store the word, basically? And then, even if you encrypt the word, how do we check that, the person who generates the hints for the word, the person who determines, or the service in most cases, whether these tiles should be, colored green or yellow or black. How do we know that they're, doing their job correctly? And so the answer is zero knowledge proofs for Mina. And so usually I kind of have the code broken up into different slides, but I actually thought it was more confusing for this example. So we'll kind of walk through this together. First, this just normal Wordle example, and then the recursion example later. So this whole project was scaffolding using the zkApps CLI, which is just an npm package that you can install. We'll have like a slide for it at the end of the presentation. And it's our only piece of developer tooling. It's very powerful and it's very simple. It's super easy to use and intuitive. Basically, we called zk project Wordle, and it created and scaffolded this whole project with things like linting, all the stuff necessary for our deployment to the networks, a GitHub repository so that we can publish this, npm stuff, testing setup, everything just works prettier. Sort of the whole thing just works. And it also adds usually an add contract. And I've deleted this in this case, but the add contract is a very simple example smart contract that you can play around with if you want to dive in. It's as simple as just npm install zkApps CLI zk space project space hello, and then open up the hello repository, and you can deploy straight to Berkeley or play around with the code, whatever you want. But for now, we'll dive into this Wordle example. So first things first, we import all of our stuff from SnarkyJS. That's pretty normal. And then I'm actually going to scroll down past this and jump to this smart contract part. And we'll kind of explain like what the anatomy of a smart contract looks like. So what we do is we just extend smart contract into a new class Wordle. And then generally we define our state up here. And so this is this state decorator basically tells SnarkyJS, hey, these are variables that should be stored on chain, and we should be able to update them. But when we do update them, we should prove that we're updating them in a legal way, basically. And so you can see that they all have different types. One is a field. This is kind of like our primitive type. And then we have this unsigned integer of 32 bits, which is something that's provided. And then we have this word type, which we'll scroll up to in a second. And this is something that we've defined ourselves using struct. So the next thing that we have generally is this init method. And this is a method that usually runs after the smart contract is deployed, but before users interact with the smart contract. And so in this case, we use this to set, to initialize our state variables to appropriate values. And there's also a deploy method that you can't see here. It just it's kind of behind the scenes until you need it to be in front of the scenes. But this is something that you can use to define like what happens when the method, when the smart contract actually gets deployed to the network. But in most cases, people won't have to fiddle with that too much. So yeah, we have our init method where we're just initializing our state. And then we have these user-defined methods, which we have this, these user-accessible methods. So we have this method decorator in front of them. And this basically tells SnarkyJS, hey, a user should be able to call this method, in a transaction. And when they do, prove that they did it correctly, generate this list of updates to the on-chain state, and do all these other kind of like housekeeping tasks. And so we have two of these. We have one for publish guess, which is going to allow the person who's playing the game to guess a word. And so you can see we pass into this our guess, which is of the word type. And then we also have publish hint. And so this will be called by either the person who's generating the hints, or in most cases, this will be just like a service. You could have, just like a Docker container running somewhere that does this. And so publish hint, again, we have the method decorator, and we pass in another word, but this time it's our solution. And so the solution is the word that the user is trying to guess. And we pass it in, but it doesn't ever get revealed to the network or anybody. This stays on the person who calls this method's machine. And so we can check that the hint is valid for the solution that we the hint that we generate is valid for our solution without having to reveal what the solution is to the rest of the world. And then that's it. So this is kind of how smart contracts are generally structured, with state up top, an init method, and then the methods that users will be able to call. Now we'll kind of jump up here again into our state, and we'll talk about what each of these things do, and then we'll jump into Word. And so solution hash is what it sounds like. It's a hash of our solution, and we use this to store a commitment to the solution so that the hint generator can't change the solution mid-game. This way we have one solution for the whole game, and we can check that we're generating hints for the correct solution without revealing the solution. We just hash whatever we pass in to solution down here, and check that it equals this solution hash that we have stored on chain. We also have a turn number, which is again what it sounds like. This is the number of turns. We use this to determine whose turn it is, so that the hint generator can't generate a hint on the guesser's turn, for example. And then we have last guess, which is the state that we use to remember the last guess that we made. And then also this gets mutated in order to communicate the hint that the hint generator has added for a given guess. And so you can see that this is of this word type. And if we scroll up here, we can see that this word type is created by extending struct, and it has this encoded word key with an array of 5 field elements as the value. And so word is in this case pretty simple. It's just basically an array of length 5 of field elements, but this could be much more complicated. We can create significantly more complicated types using this struct. The other thing that we've added is this static method from string. And what this will do is we can pass in a word, which is an actual string, like a JavaScript string, and we'll first convert this into lowercase. Then we will iterate through each of the letters in the word, and we'll check if they are this regular expression just means check if we're a letter between A and Z, and not like some sort of special character like an @ sign or a $sign or something like that. And so we test this, and if it's true for this index, then we take this encoded word array and we push onto it a field with the value of the character code of the word -96. And so we do this, this is calling character code on Word is going to basically give us back like the ASCII value for this character. And then we subtract 96 in order to, make A equal to 1, basically. And so we push this onto this array if this is true. And then if it's false, if the character is not lowercase, then we just push 1, which is in A character. And this is kind of a weird default behavior, but you could make something more complicated to catch these errors better. In this case, I've just used 1 or A as basically like the default value. So what we do then is we call Word, and we return Word with this encoded word passed in. And so what this means is that if we want to create a word from a string, we can just call this from string method on it, and what we'll get back is a word that contains this encoded string. So we'll get back a word, which is basically these 5 field elements in an array that is associated with the word that we passed in as a string. We also have a method which is hash, and so this we can call this, and what it'll do is it'll return the hash of the encoded word. And so this Poseidon is our hash function here, and we just call this hash method on it. And we pass in our encoded word, which is an array of fields. And we get back a single field element, which is our, let me see. Yeah, we get back a single field element, which is the hash of our encoded word. And so, yeah, we've now defined kind of another data type that we can work with. And we'll have last guess equal this. And so now when we jump down to init, the first thing we do is we set our solution hash. And we do this just by calling, this solution hash and then set, and passing in what we want to set it to. And so in this case, we, word from string, and we pass in hello. So now we have a word basically an array of 5 field elements that is associated with hello. And then we call the hash method on that, and we get a hash back. And so then we set this to our solution hash. And so in this case, the solution for this game is hard coded just for the sake of simplicity, but you could just as easily have this be something that's configurable using a method that checks that you're like an approved user to change the solution or something. The next thing that we do is we set the turn number to 0. And so in this case, we have this unsigned integer, and we initialize it with a value of 0 by passing in a field also with a value of 0. And we use unsigned integer for a reason that I'll get to in a second, as opposed to field, because we need one of the unique properties of unsigned integers that fields don't really provide. And finally, we'll set the initial guess to AAAAA. So it doesn't matter what this is because it won't be possible to generate a hint until the guesser updates this. So yeah, we just set it to 5 A's by calling word from string and then passing that into the set method for last guess. So now this runs and our smart contract is live. And there's 2 methods that users can call. The first is publish guess, and we'll pass in our guess, which is another word. And so there's a few things we have to do. The first is that we'll grab the turn number from the Mina network. And we do this. This is simple. We just define a turn number here, and we set it equal to calling the get method on the turn number state up here. And what this does is it basically grabs this value from the Mina network. It grabs what's the most recent turn number value, and it dumps it into this variable. Now we need another line below this, and this is something that we're maybe thinking about making a little bit more magical because it seems to confuse some people. But this line below it, what it does is it basically confirms that the proof was generated and the transaction was generated for the same turn number value that's currently live on the Mina blockchain when the actual transaction gets validated. And so this basically grabs our value for runtime. And then when it comes time to actually, submit the transaction, this basically checks that this value is still true. And so this is important because what if somebody grabbed a turn number, created a zero knowledge proof and a transaction, and then waited 5 hours and sent it later, and by that time the turn number had changed? Well, we need this, assert equals in order to basically communicate that we want we want the transaction to only be valid if the turn number that we ran it with is the turn number that's still on chain. The next thing that we can do is we can check that it's the guesser's turn, and we do this just by calling this mod method, which is something that doesn't exist on the field type, and so this is why we have to use the uint type on turn number, and then we assert that it's equal to 0 in this case. So half the time it will be 0, half the time it won't be 0, but this way we know that it's our turn if it's 0. And then the next thing that we do is we increment the turn number. And we do this just by, instead of calling get this time, we call set on the turn number variable, or I guess like on-chain state. And we just pass in our current turn number plus an unsigned integer with value 1. The final thing that we do is we check that all the values are between 1 and 26. That means that they're valid letter configurations. So we just iterate through each index of our encoded word on our guess word, and we assert that it's greater than or equal to 1 and less than or equal to 26. And finally, we set the last guess to our new guess. And so now last guess gets set to the new guess that we passed in. So this is really basically just incrementing the turn and checking that our input is valid. And now once that's done, we now have a new guess in this state variable. And it's time for we can't call publish hint we can't call publish guess anymore because this assertion will fail. We've incremented the turn number. But what we can call is publish hint. And so this is what the hint generator will call. And again, this could be a service probably in most cases. So we pass in a word again, but this time it's our solution instead of the guess. And we grab our turn number. This is the same thing we've seen. And we check that it's our turn. And we do this just by adding 1 and then exactly the same thing, mod 2, and then assert that it's equal to 0. So this will be true when this is false, and this will be false when this is true. So this is how we know it's our turn. And if this assertion fails, not only will the code exit, but you won't be able to generate a zero knowledge proof anymore. So even if you found a way to make the code run, no matter what level of the stack you fiddle with. Like even if you change the hardware of the computer to make this sort of just run through, the proof that you would get out would still not be valid. Okay, so then we increment our turn number, same thing. And now we grab the solution hash from the Mina network and we check that the solution that we pass in matches the one on chain. And so we do this just by checking, we call hash on our solution that we passed in. Our solution word has this hash method. And then we assert that it's equal to the solution hash that we just got from the on-chain state. We also grab last guess from the Mina network.
Just one note, you have 10 minutes left.
That is okay. Awesome. Thank you so much. Okay, so okay, now what do we have to do? Well, we have to check which letters should be green. So we iterate through every single index, for both the solution and the guess, the last guess, and we check if the last guess is equal to the solution for this index, and if it is, then we set is correct position to true, which is of the bool type in this case, which is again, sort of constructed out of these field types. And then if this is the case, then we add 200 to the letter in last guess, and so we use this circuit.if. We pass in, is correct position, and we select basically whether last guess, the index in that array should be updated to, either nothing, or we should add 200 to it. And so the point of adding 200 is that we retain the same number. Like if we have 7, then we have 207. So we can still tell what letter was guessed here. But now we have this 2 in front of it, which basically says, hey, 7 was a correct letter in the correct place. And so yeah, this ends with last guess being updated to have these hints for when the letter is correct and in the correct place. The next thing that we do is we have to check for these yellow letter hints, which are if the value is correct, but it's not in the correct place. And so how we do this is we iterate through every possible combination of indexes, and we check if the letters at these indexes match. So now instead of, last guess and solution both being indexed at I, one is indexed at I and one is indexed at J. And if the letters match, then we add 100 to the letter in last guess. And so we're mutating this, last guess word. If this is true, we add 100. Again, we know 100 means this is the correct letter, but in the wrong place. 200 means this is the correct letter in the correct place. And we maintain the letter in these last two places. And then the final thing that we have to do so that we don't count these letters multiple times is we basically cross them out in the solution array. And we do this just by setting them equal to 0 if this is true. That way we don't count them twice. You can imagine like every time we iterated through, we would get another letter. So for example, if we had one E that we had guessed correctly, but the word had 2 E's, or let's say we had guessed 2 E's, but the word had 1 E. Without this block here, we would get hints for both E's, even though we really only want hints for one. And so then the final thing that we do is we set this last guess to our new last guess, which includes the hints. And then now the guesser can guess again. And so there's some things that are missing here, like in terms of if you wanted this to be a cool, usable smart contract, and we've done this just for the sake of simplicity for this explanation. But we could do something like have if the user guesses the correct word in like X moves, then we pay some amount of Mina to them, or something like that. Yeah, we could have it more configurable in the sense that some permissioned user could change the word. But this is a very simple Wordle example, and we have a test for it that I think I was planning on explaining in more detail, but I think we'll kind of gloss through it really quickly because it looks like we only have 10 minutes left. We can jump into this test though still. We'll run it down here. And so yeah, SnarkyJS, I'm sorry, the zkApps CLI scaffolds all of this for you, so you don't have to worry about it too much, but it's pretty clear what it does. I won't explain it for the sake of time here, but we have our first test, which generates and deploys our smart contract. And then we get into kind of the more interesting one down here. We test things kind of incrementally. Eventually we get down here to this one, where we're going to basically do like an example flow. And so all that we do is this is something in this case is done in test, but you could just as easily do this in your front end. We take some sort of string in, we create a word from it and store it, in exile here. And then we just call on the zkApp this publish guest method, just like you would expect, and pass exile in. Then we can prove that we did this correctly, and then finally send this transaction off. We can, then grab these values to see how they've updated. And in this case, we check that they, have updated to what we expect. And then we also console log it. Or that might be, sorry, I'm one test too high. Down here, yeah, we console log these values. And so if we scroll up, we can see what this looks like. All of our tests pass. But in this case, we have the word hello as our correct word. And if we guess exile, we can see it's turn number 1. And this is what our guess looks like. And so A, B, C, D, E, E is the 5th letter in the alphabet. Here's our encoded word. And now when when the hint generator runs this, we get exile, on turn number 2. And now they add 1 for the E, 100 for the E, because there is an E in hello, but it's in the wrong place. But you can see that exile also ends with an E, but we don't add a 100 to this one because we've already, sort of occupied our correct E. We can also see that L over here, exile and hello both have L as the second to last letter. This, 12 means L, but now we have 200 added to it. And so now we can use this, your front end could use this information to color the tiles correctly. And then we go back and forth a few times until eventually we guess hello and we get the correct values. So I guess now we can talk really quickly about recursion. There is more information on this, and maybe if you're curious, come to office hours and we can talk more about this. But what recursion allows us to do is it allows us to change this smart contract from a smart contract into a ZK program, which is just exactly what it sounds like. It's a program that we can prove. But this program can take as an input, it's a proof of itself. And what this means is that now instead of playing this game, on the blockchain like we normally would, where we create a transaction, pay the transaction fee, send it, wait for it to get mined, and then the next player can make a move. We have this system where we can just send this data peer-to-peer. And by passing the last proof as an input into the next proof, we get a final proof that represents that the whole game was played correctly. And then we can pass this as an argument into a smart contract to finally settle the game. So this code is available. Like I said, there's a link to it. We'll not dive into it too much here. But basically, very much the same thing. We copied and pasted almost all of the code from the normal example to make it recursive. And we can see what this looks like to run to and we'll let this run for a second while I talk about some of the stuff at the end and come back. So you can see we're compiling the contract. And you should kind of be able to get a sense for how things work differently. So now I'll switch very quickly to our Wordle example. To our slides again. And there's 2 things I'll highlight here also. One is that we could have just as easily built this with a UI. If you're curious, tutorial 4 in the docs explains how to build this with a UI. I didn't for the sake of sort of clarity. Just that there's kind of only one thing and we don't have to wait for transactions to mine on testnet and stuff. We built a smart contract. Tutorial 4 teaches us how to, integrate it with a UI. And now we can kind of talk about, I guess, how do we get started? So so just npm install the zkApps CLI and call zk project name, make it hello or something, and you'll get a scaffold project just like this with an example add contract. How can you get involved? You can visit Mina's developer docs. There's a link to that in the chat. You can apply for a retroactive grant. You can build a zkApp. This is definitely something that everybody should do because it's pretty easy. You can get something deployed to testnet in an hour. And then finally, you can join our zk Ignite cohort 0, which is a program that has $250,000 Mina tokens associated with it. And basically, we give prizes to people who make good faith zkApps and extra prizes for people who build particular cool things. You can learn more about it from the link down here in the chat. And we also have a QR code. I think that's roughly all. There was a couple things that I didn't get a chance to do, but I'll just kind of explain are possible. I was going to deploy our Wordle contract to the Berkeley testnet, which is our basically it's the testnet of what Mina will look like after zkApp functionality is enabled on it. And then we're going to interact with it there. So you can do that if you're curious. It's pretty simple, and also outlined in, I think, tutorial 3. And then, yeah, building a UI in tutorial 4. So I think that's roughly it. Sorry, I kind of got a little bit like discombobulated at the end here, but the general idea is Mina is really cool. It's really different. You can build a lot of really cool things with it. SnarkyJS is super powerful, and it's also very easy to use. And you should explore all of these things because hopefully, you know, we're kind of opening the door to like a lot of really cool things that weren't possible before with blockchains, or even with traditional applications. Yeah, I think that's about all. Thank you so much, guys.
Oh, I see that my microphone was off. Let's jump to Q&A because there is plenty of questions over there, and we'll have to also read them up loud for the video for our future audience to see.
Cool. We have what would happen if you throw an error here. If you reply to your comment, Andrew, with where here was, I will answer that, but I don't know where here was anymore, unfortunately. Do you have a developer grant program? What should we do to apply? 001 Labs does not, but Mina Foundation has lots of information about their grant programs on their website. So that's a good place to kind of explore what's available to you there. And then for Derek, we have, looks like most statements ultimately are a call to a smart contract method or a field method, like a DSL. Is that right? Can you use any JavaScript statements? In particular, can you import and use external JavaScript libraries? So this is a good question. The answer is basically yes. I would say that the experience of using SnarkyJS ends up feeling a lot like using React or something like that, where it's not like too magical. It kind of is still JavaScript, but you're using it in sort of a unique way. But it's still very intuitive. So you can't just make an arbitrary JavaScript statement. And the reason why is because SnarkyJS won't know how to prove it. And kind of like, there's a couple different reasons for this, but the simplest one is if you have something like a string, JavaScript won't know how to represent this as a field element. And all of our information has to be represented as field elements in order for like sort of the under the hood stuff of the zero knowledge proof system to work. So yeah, what that means is that you can't just import a random JavaScript library and use it, but you can make SnarkyJS specific libraries and then import them and use them, and you'll get completely constrained code. You can also, I mean, you can just use normal JavaScript anywhere that you want to, but it won't be proven unless you use sort of a fancy trick. So like, as people get more advanced with this, there are some times where you actually will like, where you might want to, if you have like a certain kind of routine that there's an efficient way to do in JavaScript, and you have some sort of like way that you can check that it happened correctly without having to do it, then you can sort of escape out of SnarkyJS, do your thing, and then jump back into SnarkyJS and verify that you did it correctly. But this is like a pretty advanced pattern. You kind of have to like have a strong intuition for what's going on in order to be able to do this right now. Oh, for init, what would happen if you throw an error here? I actually don't know exactly what would happen. I think it depends on the context. Maybe Gregor, who's in the chat, has like a good idea. I think that if this happens on I think that if you write a smart contract, deploy it to Berkeley testnet, and then you run the init method and something goes wrong, Well, first of all, I think that the zkApp CLI should catch this before you get that far. But if you do manage to get that far, then I think that what will happen is that your transaction will just get dropped, and then you'll have to redeploy your contract maybe. I mean, I think you would want to redeploy your contract in that case. And I think that's all the questions.